Hi, in this video, we are going to look at the topic of quadratic residues. So first of all, before defining this term, what I would like to introduce is what we will do if we encounter an equation like this. It is a quadratic congruence. So for example, we have to solve this. Rx square plus Sx plus t is congruent to u mod m. This is a general quadratic congruence. It is called a quadratic congruence because you have x power is 2. In the previous video, we have seen how to solve a linear congruence. So if the question was simply Sx plus t is equal congruent to u mod m, that was something that we learned how to solve in the previous video. But because of this term, it is now a quadratic congruence, and the general form that we have here is actually too difficult to solve. Like, it is very difficult to solve it in general. What we usually do is sort of ignore this middle term. Ignore this middle term, and we think about a congruence like this. Rx square plus t is congruent to u mod m. Now, we have learned that when we want to solve congruences, we can basically subtract any or add anything to both sides of a congruence. So this implies that Rx square is congruent to u minus t mod m. And hopefully you can divide by r here. And what we will get is, you can first of all call u minus t as a v mod m. We are saying v is equal to u minus t here. And these are all integers. So now it might be possible for you to divide this by r on both sides and say something like this: x square is equal to v by r mod m by GCD of m and r, right? Now, in certain problems, this can start looking like something of this form. X square is congruent to v by r could be an integer. It can be called v dash. And this could be mod m dash, right? This could be some integer. This could also be an integer. So technically, we are trying to solve a congruence of this form. X square is congruent to v dash mod m dash, right? Now, the problem is basically find x such that x square is congruent to v dash mod m dash. That is the idea. So we have to find numbers whose squares are congruent to v dash mod m dash. Now, this idea is what gives rise to the concept of quadratic residues. So first of all, remember that not all numbers have square roots. When we deal with congruences, not all numbers will have square roots. So for example, let's think of the case where we are working in mod 6. Suppose we are working in modulo 6. What happens in modulo 6? We have actually six possible numbers, six different types of numbers. You have 0 mod 6, 1 mod 6, 2 mod 6, and so on. 3, 4, 5 mod 6, right? Now think about it. What happens if you square any of these types of numbers? So if this is my x, what will be my x square? Think of what x square is. If x is 0 mod 6, x square is also 0 mod 6, right? If x is 1 mod 6, x square is also 1 mod 6. If x is 2 mod 6, you get a 4 mod 6 here. For 3 mod 6, you will get 3 square 9, which will again give a 3 mod 6. Because 9 is equal to 3 mod 6, right? And for 4, you can write it as minus 2 whole square. 4 is congruent to minus 2. So it is congruent to again 4 mod 6. And 5 is congruent to minus 1. And that will be congruent to 1 mod 6. So what we are getting is there are only 6 types of numbers when we work in mod 6. They can either be this 0, 1, 2, 3, 4, 5 mod 6, right? And when you do squares of the 6 types of numbers possible, you end up getting these different modulo, right, for x square. So working in mod 6, x square can be what? It can be 0, it can be 1, it can be 3, and it can be 4 mod 6, right? So what this tells us that there is no possibility of x square can never be equal to 2 mod 6, or x square can never be equal to 5 mod 6, right? So what this tells us that 2 has no square root working in mod 6. So when I say not all numbers have square roots, so when you work in mod 6, the numbers 2 and 5 have no square roots. So there is no integer whose square will give us 2 mod 6. Similarly, there is no integer whose square will give us 5 mod 6. The only possible squares can be 0, 1, 3, or 4 mod 6. So a number which has a square root, a number which has a square root mod m is called a quadratic residue, is called a quadratic residue mod m. So basically the idea is pretty simple. When we worked in mod 6, how many quadratic residues are possible? We had 0, we had 1, we had 3, and we had 4. So there were 4 quadratic residues mod 6. And 2 and 5 were not possible. 2 and 5 were not quadratic residues in mod 6. So simple exercise for everyone here would be to find out all the quadratic residues, find all quadratic residues in mod 7, mod 8, mod 9. So what I will do is I will do it for mod 7, and then I will leave mod 8 and mod 9 for you guys to calculate, right? So if you think about it, 0 mod 7. If x is 0 mod 7, x square would be 0 mod 7, right? Similarly, 1, if x is congruent to 1, then x square will also be congruent to 1 mod 7. X is congruent to 2 mod 7, then x square will be congruent to 4 mod 7, right? Great. Similarly, we can calculate if x is congruent to 3 mod 7, x square will be congruent to 9, so which is 2 mod 7. And now notice one nice thing. Once we have covered these first few, like we covered the 1 mod 7, 4 mod 7, then 3 mod 7, and then 2 mod 7. Actually, I am saying it wrong. We covered the 3 cases so far. When x was 1 mod 7, 2 mod 7, and 3 mod 7. That time x square came out to be 1 mod 7, 4 mod 7, and 2 mod 7, right? Now, if x becomes 4 mod 7, obviously, you should realize that x is equal to minus 3 mod 7. So x square will be the same thing as minus 3 square mod 7, which is the same thing that we got here for 3 mod 7. So the residue here will again be 2 mod 7 for x square, right? Similarly, for x is 5 mod 7, 5 is same as minus 2. So whatever residue we got for 2 mod 7 will repeat here. So we will get a 4 mod 7. If x is congruent to 5 mod 7, x square will be congruent to 4 mod 7. And similarly for 6, you will get 1. Because 6 is minus 1 mod 7. So x square would become minus 1 square or 1 mod 7, right? So what pattern I want you to notice is that the residues are, for mod 7, the residues are 0, 1, 2, 4. And what happens is 1 was coming here, the quadratic residue was 1, then 4, then 2, and after that it was again 4, 2, and 1. The reason for this repetition is because when x was 1 mod 7, its residue, its quadratic residue will be the same as it would have been for x is equal to 6 mod 7. Because 1 and 6 will 6 can be written as minus 1 mod 7, and when you square, it has the same residue, right? Similarly, 2 and 5 will have the same quadratic residue, and 3 and 4 will have the same quadratic residue. So you should notice that there is some sort of a pairing that is happening here, right? When you have mod 7. So the total number of quadratic residues mod 7 are only 0, 1, 2, and 4. So what does that tell us actually? This tells us that any number which is 3 mod 7, for example, you cannot have a square root in mod 7 for that, right? So basically, you cannot have a solution to the equation x square is congruent to 3 mod 7. You cannot have a solution to an equation x square is congruent to 5 mod 7. There is just no such integer which gives x square is equal to 5 mod 7 or 6 mod 7 for that matter, right? So the answers for these, I will just tell you. The quadratic residues for 8 are 0, 1, and 4. And the quadratic residues for 9 are 0, 1, 4, and 7. These are the different quadratic residues in all of these cases. Now, one simple point that I would like to make, you can verify this by taking different examples. The number of quadratic residues mod n for an even integer n is equal to 2m is possibly up to m plus 1. So basically, this is the, I forgot to say, maximum number. The maximum number of quadratic residues for an even number n, where n was equal to 2m, is m plus 1. You can confirm this by checking some even numbers. For example, for 8, we got the residues for 8, right, in the previous problem. The quadratic residues are 0, 1, and 4. So now notice that the maximum number allowed is 4, and you got 3. So sometimes you might not hit the actual maximum number, but the maximum possible residues are always m plus 1 for even numbers. The second point is for odd numbers. For odd numbers where n is equal to 2m plus 1, the maximum number of residues, quadratic residues, is again m plus 1. So in both the cases, for even or odd numbers, the maximum number of residues is m plus 1. However, in this case, you can write it as m plus 1 is technically n plus 1 by 2, right? This is the maximum number of quadratic residues for an odd number. And one more point that I would like to make is if P is a prime, other than 2, right? In that case, it is basically it is an odd prime. Then it always has the maximum number of quadratic residues, which is equal to P plus 1 by 2 whenever you do a mod P calculation, right? So for any odd prime, so far we were working with mod n here, right? Here n was not a prime. N could have been even, odd, whatever. But if you work in a prime modulo and it is an odd prime, the number of quadratic residues in that is always equal to this. It is the maximum number and it is always equal to this. You can again confirm it by looking at mod 7, right? If you recall, we calculated all the quadratic residues for mod 7 and we calculated it out to be 0, 1, 2, 4, right? What does that mean? Notice that 7 is n, or it is P. So So p plus 1 by 2 is equal to 4, and we are getting 4 residues. So for odd primes, you always get the maximum possible number of quadratic residues, which is n plus 1 by 2. However, for even numbers or for other odd numbers which are not prime, you may not hit the maximum number of residues. Your actual residues might be lesser than that, right? So those are 3 facts that you can verify with some calculations. However, one last point that I would like to make here: what is the purpose of this discussion? Why are we talking about quadratic residues so much? It is not just because we want to solve a congruence like this. Not just because sometimes if you want to solve a congruence like this, you might need to use this residues, right? The other important idea is by knowing about quadratic residues, we understand special cases of numbers which aren't residues, numbers which are not residues. So what is the meaning of that? So basically, what we realize is, for example, if you work in modulo 4, right? Take all the squares in modulo 4, 0 mod 4, 1 mod 4, 2 mod 4, and finally 3 mod 4. If you take all the squares in all these cases, you will realize here you get 0, here you get 1, here you get 0, here you get 1 modulo 4, right? So the only possible quadratic residues in modulo 4 are 0 and 1. Why is this fact important? This means that any square, basically x square, can only have the form 4k or 4k plus 1, right? No square can ever have the form 4k plus 2 or 4k plus 3, right? Because we know that anytime we square any integer, the only quadratic residues are 0 and 1. You will never get a 2 mod 4 or a 3 mod 4 when you square anything in modulo 4, right? So all squares will only have the form 4k or 4k plus 1. So that is an important fact that will be useful in certain problems. So it will help you establish contradictions, right? Similarly, there are some other facts like that. For example, squares, when you take mod 3, the only possible residues are 0 and 1 again, right? So no square can ever be 2 mod 3, correct? Similarly, squares modulo 8, squares mod 8, the only possible residues are 0, 1, and 4, right? So what this tells us is an alternate strategy to prove that some expression cannot be a square, to prove that some expression cannot be a square. We get an alternative method. We can just try to show that it is congruent to, possibly you can say 2 or 3 or 5 or 6 or 7 mod 8. If you can show that that expression is congruent to 2, 3, 5, 6, 7 mod 8, then it is not fitting in the 0, 1, 4 residues that mod 8 is supposed to give us, right? So then it establishes a contradiction, and we can show that it is not a square. Or you can even show that it is of the form of 2 mod 3. If it is of the form of 2 mod 3, it cannot be a square, right? So that is the main idea of quadratic residues. You know special cases of when x square can have a certain form in a certain modulo, right? And that will help you in your proof solving. When you have specific questions, you can check or set up a contradiction using these facts that you are now aware of. So hopefully you have understood the idea of quadratic residues, and you can try and calculate those residues for different integers. and try and use this in problems. So we will see examples of this as we go along, but I hope the concept is pretty clear. That's it for this video. I'll see you next time.